Assalamu alaikum, my dear respected student. Today I'm going to here to explain the continuation of the previous lecture of the carboxylic acid. In today's lecture, we are going to discuss the derivatives of carboxylic acid like synthesis of carboxylic acid anhydride, their reactions. Then next we will discuss esters, their synthesis and their reactions. So let's move on. First, I'm going to discuss that how carboxylic acid anhydride could be synthesized, right? The first method, which is very common and very easy method, when carboxylic acid reacted with the acetyl chloride in presence of pyridine. Pyridine is a solvent as well as the strong base. The property of the pyridine is that during the reaction, the acid formed will be neutralized by the pyridine to give you the pyridinium chloride. So ultimately, what happened when these reagents are reacted with one another, and acid react with the acetyl chloride to ultimately generate the corresponding anhydride along with the pyridinium chloride, which will be separated, and we get our required carboxylic acid anhydride. Second method is when sodium salt of carboxylic acid reacted directly with the acid chloride to ultimately afford the formation of acidic anhydride, right? Now, what happened? Another method that how the acidic anhydride or acid anhydride could be synthesized is the easiest way of the reactions of dicarboxylic acid compound on heating. For example, succinic acid, it's an example only. When reacted or heated at high temperature like 300 degrees Celsius, the dehydration take place to ultimately afford the cyclic ester. And we have this specific name of this molecule is succinic anhydride. Another method like phthalic acid, which is again a dicarboxylic acid compound, when heated at 230 degrees Celsius, we can afford the phthalic anhydride, which is 100% yield along with the water molecule, which is dehydrated. So these are some common methods by which the acidic anhydride could be synthesized. Now let's move on the reactions of acid anhydride. The first reaction of acid anhydride, what happened? The conversion of acid anhydride into carboxylic acid. Here, when the corresponding or the given acid anhydride when dissolved in the aqueous solution containing the catalytic amount of the acid is being converted into their respective carboxylic acid. It is very common reaction of the hydrolysis of the ester. The mechanism is quite simple. We know that the acid anhydride, the oxygen is nucleophilic from its oxygen. When it is dissociated into the aqueous solution containing the catalytic amount of acid, the oxygen will capture the proton from the acid, and ultimately we have this protonated form of the acidic anhydride. By this way, this carbon become more reactive. Even a mild nucleophile can attack over this carbon or its reactivity will increase. In the next case, the water, which is of course a base as well as the nucleophile, will attack as a nucleophile on this electron deficient carbon because now it is more reactive to ultimately afford this tetrahedral intermediate, and we have the oxonium ion as well. Now what happened? The lone pair at this oxygen will capture the proton to give you this intermediate. It is just the intermolecular proton shifting to give the oxonium ion. And we have the diol as well. Diol, they are very unstable intermediate and they immediately wanted to cleave in order to give you the stable molecule. And this protonated Oxygen also um, just giving the forward direction reaction to cleave this carbon oxygen bond as well. Now this lone pair will collapse, and uh, in this collapse of the lone pair, the carbon oxygen bond will be cleaved ultimately, and we have this protonated carboxylic acid along with the another carboxylic acid. Now this proton will be captured by the water molecule, while because we are using in this reaction the acid as a catalyst, which will be regenerated to ultimately afford the carboxylic acid. Now, this is the method that how esters could be converted into the corresponding carboxylic acid. Next one, that the carboxylic acid the ester could be converted into the other carboxylic acid. How? When esters are reacted instead of water in alcohol, we may achieve the carboxylic acid along with the ester instead of both carboxylic acid. You see, the solvent plays an important role. If we are using water in the previous case, we are having the two carboxylic acid molecule. But in this case, if we are using the alcohol, we are obtaining the one carboxylic acid molecule and the other the ester molecule. Similarly, if we treat the ester with the secondary amine, we may achieve the amide and the substituted alkyl ammonium substituted alkyl ammonium acetate as well. Let's see some more synthesis of esters. Uh, how ester could be synthesized. For example, this is the second part. Previously, we are discussing the anhydride. Now we are moving toward the synthesis of ester, means the conversion of less reactive group towards the more reactive group slightly require the temperature. The common reaction is when carboxylic acid reacted with the alcohol in presence of a catalytic amount of the acid, we may achieve the ester and the water molecule. Very common reaction that when carboxylic acid in place of the catalytic amount of the acid is being reacted, first step is the protonation step to make this carbonyl carbon more reactive, right? We are just activating this carbonyl carbon. Now, this alcohol, which is not the good nucleophile, but because now this carbonyl carbon become more reactivated on protonation of this oxygen, and this carbon is more electron deficient as well, even this alcohol oxygen will act as a nucleophile to establish this tetrahedral intermediate. Now, this intermediate contained the oxonium ion, which is highly acidic in nature, and we have the diol as well, which are basically, the basic in nature. So, intramolecular proton shifting take place to give you this oxonium ion and this OH. It is because now this lone pair will collapse to remove this water molecule, and ultimately we have this the protonated ester along with the removal of the water molecule. This water molecule will capture this proton to generate the acid catalyst again. And we have our required ester as well. This is how ester could be synthesized. Some more synthetic route of esters are when benzoyl chloride reacted with ethanol in pyridine, we may achieve the ester along with the pyridinium chloride. I have already explained that pyridine is a strong base and a good nucleophile as well, and it is also used to neutralize the acid formed during this reaction as well. In this specific example, when benzoyl chloride is reacting with ethanol in presence of pyridine, we ultimately afford the ethyl benzoate, which is an ester, along with this salt. Next example, that anhydride, when react with the alcohol, we also may achieve the ester as well. In this specific example, this is the acidic anhydride, which is reacting with benzyl alcohol, which ultimately giving you the benzyl acetate along with the corresponding acetic acid. Now, there are some base protonated hydrolysis of ester, which is also known as saponification. In this case, what happened, we can consider these are the reaction of ester. Means when ester react with strong base, they ultimately give you the sodium salt of carboxylic acid along with the alcohol. While because base act as a nucleophile, and which ultimately result in the removal of this alkoxy group, which will capture the proton from the solvent to give you this alcohol and the sodium salt of carboxylic acid, which on acidic workup can give you again the corresponding carboxylic acid. The mechanism that how what happened this reaction, this in the basic medium, base will serve as a nucleophile and attack at this carbonyl carbon to afford this tetrahedral intermediate. Now this oxyanion will collapse to ultimately remove this alkoxy group to give you this alkoxide and this corresponding carboxylic acid. This is very strong base. It will not stop here. It will capture the proton from this carboxylic acid to ultimately give you this salt of carboxylic acid along with this alcohol, which on usual acidic workup will ultimately converting into the carboxylic acid. This is how the ester could be converted into the carboxylic acid. It means it is a two-step reaction. The first step, the reaction with base to give you the salt of carboxylic acid, and the second step, the reaction with the acid, or we can say the acidic workup to give you the carboxylic acid. Similarly, ester under acidic condition can also be hydrolyzed back to give you the corresponding carboxylic acid and alcohol. Very simple mechanism that in the first step, the ester reacted with the proton to give you this protonated form of the ester, then which is also making this carbonyl carbon more activated and more reactive. Even alcohol, even water can attack at this carbon to give you this tetrahedral intermediate and the oxyanion. Now, intramolecular proton shifting take place to this alkoxy group capture the proton to make this good leaving group. This diol, one of the oxygen will collapse the lone pair to release or to depart this alcohol, and along with we can achieve the protonated carboxylic acid. Now, water molecule will capture this proton to generate the acid catalyst, and ultimately we can have the carboxylic acid. This is how carboxylic acid could be synthesized from the ester under acidic condition. Means you can see the difference between the uh, basic condition and the acidic condition. That basic condition, we cannot get the carboxylic acid directly. We first achieve the carboxylic acid salt, then which is on usual acidic workup will give you the carboxylic acid. While in acidic condition, the ester directly giving you the carboxylic acid in single step. Lectons are also known as the cyclic esters, in which the gamma or delta carbon undergoes an intramolecular esterification to give you cyclic ester known as the gamma or the delta lectons. So we generally can say the lectons are the cyclic ester. Let's discuss the how cyclic ester could be synthesized. This is an example of the delta hydroxy carboxylic acid. For example, this is the position, this is the carboxylic acid, and in trivial naming, the first carbon is known as the alpha carbon, this is the beta carbon, this is the gamma carbon, and this is the delta carbon. Now, in order to get the stable molecule through intramolecular cyclization under the presence of the strong acid, this hydroxyl group will attack as a nucleophile at this carbon, and this pi bond will capture the proton from the acid to give you this six-membered cyclic structure. Here on oxygen we have the proton which is on this hydroxyl group, while this carbonyl oxygen is being converted into diol, and we have this intermediate. Now, ultimately, in this second step, the intramolecular proton shifting take place in order to dehydrate this diol. This hydrogen is being shifted over this hydroxyl group to afford this intermediate. Now, this is the oxonium ion. Now, what happened? This lone pair of the hydroxyl group will collapse over here to depart this water molecule in the form of H2O. So, ultimately, give you this intermediate, which is basically the protonated form of the cyclic ester along with the water molecule. In the next step, the water molecule will capture this proton from the oxygen of the ester to regenerate the acid, and we can have the a cyclic ester, because this was obtained from the delta hydroxycarboxylic acid, and that is the reason that we can give the name to this cyclic ester, the delta lactone. Also, you can calculate the position of the delta Y, because this carbonyl carbon, the first carbon is the alpha, this is the beta, this is the gamma, and this is the delta carbon. So, because it has the delta carbon, that's the reason this cyclic ester is known as the delta lactone. Uh, Lactones are easily hydrolyzed, means cyclic ester are easily hydrolyzed under the acidic condition to the corresponding carboxylic acid and the alcohol under a very mild condition. That's all for today's lecture, and we will be with you with more interesting lecture of the chemistry related.